In this chapter, we'll look at modeling mechanical systems. The objectives of this short video are the following. We'll be understanding the basic mechanical systems and components. We'll talk about linear spring mass damper systems, rotational spring mass damper systems, talk about combined linear and rotational systems. We'll look at geared systems, and we'll derive the governing differential equations. We'll graphically illustrate these differential equations and finally use Simulink to model these mechanical systems. Let's look at linear mechanical systems. The basic elements of a linear mechanical system are linear springs. Spring is schematically represented like this. The concept of the spring is this. So if you apply a force F and both the ends of the spring move by x1 on this side, x2 on this side, and let's say x2 is greater than x1, this means that the spring is in extension, then the force in the spring, I should say the magnitude of the force in the spring, Fk, is given by k times x2 minus x1. K is called the spring constant. Now if you notice here, since x2 is greater than x1, this quantity is positive. If you exert this force F, which is equal to Fk on the spring will exert an equal and opposite force on you right here. So Fk is in fact in this direction, and it is equal in magnitude to F but opposite in direction. On this side of the spring, the same force will be exerted in this direction. So if the spring is in extension, it will try to pull inwards. If the spring is in compression, it will try to push outwards. The damper is just like a spring, but while as the spring stores energy, a damper dissipates energy. A damper is schematically represented like this. And let's say if you exert a force F on a damper, and let's say one end moves at x2 dot, speed x2 dot, this other end moves at speed x1 dot, and let's assume x2 dot is greater than x1 dot, which means that this damper is being pulled apart. The force in the damper, or the magnitude of the force in the damper, is given by B times x2 dot minus x1 dot. Here B is the damping constant. Notice that this quantity here is positive. So the force in the damper depends on the relative velocity of the ends. So velocity or speed at this end minus speed at this end. That's right here. So this is the relative speed, or you could think of it as a speed of expansion. Finally, we come to Newton's second law. Newton's second law relates the motion of a body to the forces that are applied. So let's say you have a mass m, and there are forces Fa and Fb acting on it, and due to these forces the mass accelerates in the x direction by x double dot. X double dot is the double derivative of the position, and similarly in the y direction it accelerates by y double dot. Then mx double dot is given by sum of all forces in the x direction, and my double dot is given by sum of all forces in the y direction. Now this set of arrows here, this x hat and y hat, is an inertial frame of reference. These equations only hold in an inertial frame of reference. So you could think of the inertial frame of reference as a triad, a three axis and an origin that is attached to the ground for all practical purposes. That's your Newton's second law. Now let's look at rotational systems. Now let's look at rotational systems. The basic elements are rotational springs. So the concept of rotational spring is somewhat similar to the linear spring, but the rotational spring gives you a torque. So let's say if there is a torque tau, torque is a twisting force, and let's say this end rotates by theta 2, this end rotates by theta 1, and now this rotation in the counterclockwise direction is considered positive, and let's say theta 2 is greater than theta 1. The magnitude of this torque tau is given by k times theta 2 minus theta 1. That is the torque, magnitude of the torque in the spring. K is called the rotational spring constant. Similarly, you have rotational damper spring. Rotational spring stores rotational potential energy. Rotational damper damps out energy. So it's just like the linear damper. Let's say you have a torque tau, and this top end here twists at theta 2 dot. This is angular velocity. Theta 2 dot is the derivative of theta 2, and similarly the bottom end here is twisting at the rate of theta 1 dot, and let's say theta 2 dot is greater than theta 1 dot, then the magnitude tau of tau is given by b times theta 2 dot minus theta 1 dot. B is called the rotational damping constant. This theta 2 dot minus theta 1 dot is the relative twisting speed of the damper. And at the end of everything here, you have Euler's law of motion, which is the equivalent of the linear Newton's law of motion. And for that, we have in place of the mass, what we will have in the rotational system is the moment of inertia, and is generally denoted by J. And if you have torques, all these torques acting on this body, rotational body, then Euler's law of motion says J times theta double dot is angular acceleration, is equal to the sum of all torques, which in this case it is tau A minus tau B. So tau A, as you see, is in the counterclockwise direction, tau B is in the clockwise direction, therefore it's negative, tau A is positive. So J theta double dot is sum of all torques, which is tau A minus tau